Alright, welcome back. We're going to start looking at special aspects of triangles. We're going to start with special triangles. I'm not really going to get too far into these. These are just two triangles that are used in like the unit circle and whatnot. And this is the relationship to their sides and the angles that they are talking about, 45, 45, 90 and the 30, 60, 90. So yeah, you probably will need to memorize these in some way, shape, or form. Just know that they are there. But moving on to altitudes and orthocenter of a triangle. So the altitude is a straight line through a corner and its opposite side, making a 90-degree angle. So let's look at an example of this. If we go from CAB and we go to the opposite side and we hit at a 90-degree angle, the line through all of this is a altitude. We may need to extend the side to accomplish this. So this is where altitudes get kind of strange. So if we go from angle C to hit this side AB at a 90-degree angle is impossible. So what we have to do is we have to extend this line out further to BF. Now, coming from point C, we can hit that side at a 90-degree angle. So again, we just extend the line through. And I chose this triangle specifically to drive this point home. The orthocenter, where all the altitudes meets, does not need to be inside the circle. It can be outside of it. So just know that that is a possibility. For medians and centroids then, a median is a straight line segment from a corner to the center of the opposite side. So for example, we're going from C, we're going to its opposite side, and we're just hitting it right in the center. So we're splitting AB into two equal parts, AF and FB. That's what these lines represent, is that we're splitting each side equally. The centroid then, which is the intersection of all the medians, is the balancing point of a triangle. So you can actually do this. You can, if you have students, you can make a cardboard triangle, find the centroid, put a dot there, and theoretically, if you measure correctly, you should be able to put your finger there or whatever, and the shape will balance there. Additionally, the portions of each median have a 2-to-1 ratio. So every time you cut a median by the centroid, so AG to GD, that's a 2-to-1 ratio. And then note that all triangles created by a median have the same area. So this triangle here and this triangle here are the same area. Moving on, perpendicular bisector and circumcenter of a triangle. So really, at its base, this is saying that a circle can be drawn and all 3 points on the, or all 3 corners of the triangle will lie on the edge of the circle. So a perpendicular bisector is a straight line segment that extends from the midpoint of a side at 90 degrees. So example, line EG hits side CA at 90 degrees. So right here. So this line right here hits this at 90 degrees. And we could extend this line out further. I erased the extended portion of it to demonstrate that they're meeting at the circumcenter. So the circumcenter is the center of a circle if drawn around the triangle, and also the intersection of all of the perpendicular bisectors. Additionally, the radii are the length from the circumcenter to a corner, and this kind of gets into the point I was talking about earlier, that the corners all lie on the edge of the circle. Angle bisector. So instead of the perpendicular bisectors here, so this was like splitting each side at a 90-degree angle. This is splitting the angle. So angle bisector is a straight line segment that splits an angle in two equal pieces. The example is CJ. So J's over here. I've colored the letters to differentiate them. We'll talk about that in a second. So angle bisector CJ splits angle ACB, which is right here, into two equal parts. The incenter is the point at which all these angle bisectors meet. And what can be done here is this is actually the center of a circle that could be drawn inside the triangle such that the radii make a 90-degree intersection with each side. So if we drew a radius and it hit the side of this triangle, it would hit at 90 degrees. And that means we can draw a circle inside of it to perfectly hit each side at a tangent. So an example is radius GE from incenter G intersects side AC at 90 degrees. The incenter is also the intersection of all angle bisectors. We talked about that earlier. And then note that all angle bisectors create a useful ratio. So HC over CA, so this length here divided by this length here, is the same as HB divided by BA. The last note I want to make about this is that don't be confused between the radii and the angle bisector. There's a reason that I've color coded this. Yes, they can be very close together. They are not the same point. And then next we will move on to the next piece.